excited to be here today, and thanks for joining this session. So my name is Harmke Alkemade, and I'm here with my colleague Andreas Kopp. We are both working as a cloud solution architect for the Azure AI technologies at Microsoft, which means that we support some of the big enterprise customers implementing AI at scale using our Azure platform and the AI services that are available on that. For today, we prepared a session on federated learning with both Azure Machine Learning and Nvidia Flare, which is based on some of our experience and also some of the customers that we have been working with. So excited to share that with you today. So the agenda of the session, we will start to set a bit of context with a general overview on medical imaging with Azure Machine Learning. Then I will hand it over to Andreas for an introduction on federated learning. And Andreas will also introduce the interesting use case that we have prepared for you today, which is on 3D brain tumor segmentation using a data set that is publicly available. So yeah, if you're interested to try it out later, you can do that as well. And we will close the session with our demo on federated learning. So with that, let's start with the introduction on medical imaging with Azure ML. So I think the first thing I want to highlight is that any of the technologies that we will be showing today can actually be applied in any industry or imaging scenario, I would say. But there are some specific components that make medical imaging really interesting to work with at least from our perspective, and maybe that are interesting to highlight with you before continuing with the session. So one example is, of course, the responsible AI components that are important when working with medical imaging data. I think this should be straightforward, that we should protect the patient's data of the images that we work with, and that there are strict regulations in place, which also are different in different areas of the world, that we should take into account when working with this sort of data. But also the data itself can be quite challenging. And I think this will get clear when we will learn more about the use case of today. But often you see in medical imaging data that it has a very high resolution and a lot of dimensions to work with, sometimes even a time dimension as well. If we think about certain patient scans, for example. And there's also a challenge around labeling, which is related to some of the clinical protocols that would, for example, describe that multiple medical professionals have to agree on a certain diagnose or object that can be found in an image before we can include the label in a training cycle. So that's also something to take into account. Then we have the topic of visual distractors. So this means that there would be certain visual artifacts in the images that we are working with, which are correlated with the target label that we're trying to train in our model, but are not actually the features that we want to train on. So for this, it's actually important to look at explainability in our model to verify which areas of the images are actually being trained on, and if these are the correct ones. Which also relates to the next point, which is that explainability is really important in these medical imaging scenarios. So not just for these visual distractors, but also for user acceptance in general, to make sure that these medical professionals actually trust the models that we are creating, and also from a regulatory perspective, this can be required. So with that, taking all of these challenges into account, we can basically create this end-to-end machine learning lifecycle that we can use to train and deploy our machine learning models, and make sure that we can have an impact with the machine learning that we do on our use case. And this lifecycle would start with data preparation, where we are collecting the data, we are cleaning it, and maybe applying some transformations that are necessary before working with it. A different step is model building, where we look at our choice of tools. We do some maybe small experiments, local testing, to make sure that we can select the right tools to get started with. And then we move ahead to the stage of model training. And for this, we can go for a code-first approach. This is what you will mainly see today, but there are also low-code options available. And then we have the next stage of model registration and management. So we think that version control is really important in this stage, and not just for the actual code that you're using to train, but also versioning the actual models that you are creating, so that it's really clear what is the end-to-end lineage of the model that you have running in production. And then the last step is to actually deploy your model into a service that can be consumed from any sort of application, or however users would like to consume this information. So for this, you could deploy your model as a real-time endpoint, but also use a batch inferencing approach. And of course, monitoring is an important topic here. And if we look at this end-to-end life cycle, then Azure Machine Learning could be a platform to implement a large part of this overall life cycle. So you would start with ingesting your data to make sure that it's stored on a data source that makes it available to consume it. So for today, we are working with the unstructured imaging data, of course, but it could also be the case that you're working with more structured data like tabular data. And after ingesting that on a data store and connecting that to Azure Machine Learning, then you could decide which of the authoring experiences you would like to use for building your model. So here we have the spectrum from the no and low code solutions for developing your model, like automated machine learning or the visual designer to basically drag and drop the training process of training your models. But on the right side, there's this full code approach with Visual Studio Code and the Azure Machine Learning CLI. And for all these tools, we have the responsible machine learning tools underneath them as well, like the responsible AI dashboard, where you could identify potential bias in your data. And MLOps is also an important topic throughout the whole platform. So making sure all the assets are tracked and the whole end-to-end pipeline is reproducible. And on the right side, we have the consumption of the machine learning models. So for that, in Azure Machine Learning, there's the option to deploy it as a managed endpoint, which can be both for real-time deployment or online, as we call it, and for batch inferencing. And that's basically how you would consume the model. And then to connect it back to medical imaging. So to make it a bit easier to understand how Azure Machine Learning can be used in medical imaging scenarios, Andreas and I have been working on a repository where we collect different examples that basically do medical imaging use cases on Azure Machine Learning. And we already published our first article around this in December 2021. This is when we first published this repository with some of these initial use cases. But ever since, we have been adding more use cases to the repository and publishing some other articles that go in depth on one of these use cases as well. And the use cases itself, they range from more custom PyTorch development, but then maybe using the scalable compute on Azure Machine Learning. But on the other side, we also have some use cases that leverage automated machine learning for images. So this is a bit of a different approach. Some of the most recent additions to our repository can be found on the right side. So we have one scenario focused around 3D brain tumor segmentation from a notebook, so more like the classical machine learning approach on how you would do this use case. And on the other hand, we also have an example in this repository on how to do federated learning, which can be interesting for cross-organizational training. So if you have multiple hospitals with their own private data set and you still want to create a common machine learning model. And in the session of today, we will actually combine both of these examples and you will learn about them more at a later stage. So with that, I like to hand it over to Andreas for the introduction on federated learning.
Thank you so much, Harmke. So let me share my screen. Can you see my screen? Can you hear me?
Yes. One second. Let me make sure that the presenter is changed over.
Okay.
And now you should be able to share your screen.
All right. You can see the slide, right?
Yes.
Perfect. Yeah, then let's take a look at the federated learning concept first. Then we will take a deep dive look at the 3D brain tumor segmentation use case, how it's classically trained and developed. And then after that, Harmke is going to show the side-by-side comparison between a centralized training, classic centralized training, and the federated learning. But let's get started by looking at the federated learning concept first. So assume we have a hospital like this memorial hospital here, maybe a kind of medium-sized general hospital. And they have some patient data, obviously, because of their patient history. And they are interested in training a machine learning model to predict the outcome of a treatment, for example. Of course, they have a few data points, but in order to have really high quality, robust models, we need, as we all know, extensive and also diverse data. Diverse data means we want to be representative when it comes to the population, like we want to be representative when it comes to age, gender, ethnic background, and also medical preconditions. So here, in particular for rare diseases, it can be relatively tough, even though if the overall data set appears to be large, if we then look into those cohorts, might still not be enough data points. So the result of such a model could be maybe it's okay, but it's not really good. But of course, the Memorial Hospital is not the only hospital. So there are many, many more institutions which have similar data and also similar questions to answer, like here in this case, 2 further hospitals. So one thing that's really obvious would be, okay, we have similar data, we have similar problems. Let's just pool the data and train common machine learning model. So it would look like this, for example. So one of the hospitals, for example, the Memorial Hospitals would offer to train the model, would ask the other 2 hospitals to provide the data. And then we would expect, based on all our experiences when it comes to machine learning, that the model would be of better accuracy, more robust, and also in particular better for, let's say, underrepresented cohorts or rare diseases. The problem is that this is often not happening in practice because of data privacy concerns. So in particular, when it comes to medical data, patient data, this data is highly protected for very good reasons by regulations, by data privacy laws like GDPR, for example, HIPAA, and there is a lot of uncertainty when we talk to representatives of hospitals, for example. Are we allowed to share the data? Do we need patient consent? What happens if somebody, after giving consent, changes his or her mind? So there are a lot of questions, and this is the reason why, even though everybody agrees it would be beneficial to do that, it simply doesn't happen, or it happens very, very rarely under some very restricted circumstances. And what federated learning is doing is exactly addressing the problem. So the hospitals will still be able to train this joint machine learning model, but no participant needs to share data for that. So it's really the idea multiple parties train collaboratively without sharing data as it's expressed here. And yeah, how does it work? There are different ways to do federated learning in this, let's say, kind of enterprise scenario. typically one of the hospitals, could also be an independent institution, who orchestrates the process. So there is a concept of a federated server which orchestrates the overall process, the federation, and also provides a global model. At the beginning, the global model is just a naked model architecture, like in every machine learning or deep learning use case with randomly initialized weights. The idea is then that this global model is distributed to all of the participants, to all of the sites. Then in parallel, each of the sites, so the 3 hospitals in our case here, are training on this copy of the global model with their local data. And the training happens only on-site, on premises, or in their cloud environment, whatever. Different options are available. But the point is that the private data, the hospital-specific data, never leaves their area of control or their premises, for example. This training is happening in rounds. Each round, for example, could be 1 epoch, but there are other settings also possible. After 1 round is finished, each of the hospitals provides what it has learned, technically speaking, the learned parameters or the learned weights, to the federated server. The federated server is then aggregating those weights or those parameters, and then the next round starts. So the new version of the model is then distributed to the participants, which means we are not talking about different models. So it's always the same model, but at different points in times, or different iterations of the same model when we talk about global model or local model. So the local models are actually copies of the global model. And to be a little bit more specific in the mechanics, how such a federated training round works, as indicated here, we have the server, which is responsible for aggregating the weights, but also responsible for orchestrating the whole process. So you will see this in Harmke's demo. The server is actually instructing the clients, now train the next round, now provide your weights, for example. So, but step by step. So the server provides the global model. In this case, we have 3 hospitals, 3 clients. So there will be 3 copies of the model. Then the local training for each client is starting. In this case, we are just looking at the green hospital. So the green hospital just received the copy of the global model and is using its local data and only its local data during the training process. The local data is never shared. It then, after the round is finished from the perspective of the green hospital, it then aggregates or sends the local model update, so what was learned locally, back to the server. And this is done by all hospitals which are participating in the federation. The server is then aggregating the weights. We will see which options for aggregation are available, but this can be as simple as just averaging or weighted average. And then based on this aggregated model update, the next iteration of the model is produced, which is then sent back to the clients, and then the next round begins. So from a conceptual point of view, from the workflow point of view, relatively straightforward. We can continue this process until we are satisfied with the results, until we have good conversions, for example. But federated learning can also be used in a kind of, let's say, continuous learning process, because during the daily operations, of course, new data points are generated. So we can also see this as a continued process. New data comes in and we are continuously improving the models. So that's a question of the specific use case of the specific setting. And In terms of options or considerations when it comes to federated learning, when we look at the participation scenarios, there are two very distinct use cases of federated learning. So if you have a smartphone, you probably are participating in federated learning already without knowing it. So federated learning comes from the smartphone or consumer world. So like use cases like for your next word prediction for smart keyboards, for example. This is typically done in federated learning, so where each device represents one user, for example. So these are scenarios that are kind of fragile in terms of participation. We have maybe millions of smartphones participating in this federated learning setting. They can drop out. They have limited network connectivity. So this is more the consumer use case. This is where federated learning started, actually. And then we have those more enterprise scenarios, which are called cross silos, where you maybe have 10 or maybe 100 institutions. So there is a kind of a joint project. There is an agreement on the use case, obviously. Those participants, they have a dedicated IT infrastructure. They have resources. They have bandwidth. So it's a kind of a stateful process, so much more controlled compared to the cross-device scenario. In terms of topologies, in particular when it comes to enterprise scenarios, we have aggregation server in the middle orchestrating the process. There are also serverless architectures possible, like peer-to-peer scenarios, but that's rare in those enterprise scenarios. But it's possible. When we look at parameter aggregations, we will take a closer look at these options in a minute. But maybe thinking about benefits and limitations in general. Obviously, federated learning, the main benefit and the main driver is it addresses these privacy and intellectual property challenges. And it is also, of course, an enabler. If you think of a hospital who would say we would never be willing to, we are interested to participate, but we cannot share data. So this, of course, motivates participation in terms of user, in terms of organizations. So we can see this as an enabler for increased participation, which means we are able to address new use cases like rare disease research or also precision medicine, where we simply benefit from diverse and heterogeneous data. Of course, there are also limitations. So the federated learning process, it protects, it's a data, it's a privacy preserving mechanism when it comes to that it's not necessary to share data. The training process is kind of protected, but the resulting model is just a normal machine learning, deep learning model. And whatever the model learned, whatever the model might memorize is subject to model inversion and membership attacks as every deep learning model. So federated learning does not protect here in this case. And of course, if you think of data annotation consistency, Harmke already managed how important this is for medical imaging, but also in other settings. For example, when we talk about segmentation, here we are talking about different institutions doing the data annotation, because not only the data is local, but also the labels are local, which means we have to really carefully define how we want to label data to ensure consistency, which can be quite complex. And since we don't want to share data by definition in federated learning, we also don't have normally don't have a central data set that we can use for EDA or as an evaluation data set. Sometimes organizations make compromises so that they say, okay, let's have a subset of data as a joint data set. But the general idea of federated learning is, of course, that data is not shared, which limits, of course, things like EDA and also validation. These are some limitations associated with federated learning. When it comes to the more technical part of parameter aggregation, there are a couple of algorithms. So The most basic one is called Federated Aggregation. This is what the server is doing. It's very popular, very intuitive, so that the weights that are sent back from the clients to the servers are just aggregated, averaged, but maybe it's a weighted average, which means that the number of data points are considered. So in this example, we have 3 hospitals. 2 hospitals are based on 100 data points each, and then the second, hospital B, is based on 200 data points, and this would mean the weights are 25% for A and C and 50% for B in this case. There is also the consideration, Federated Learning assumes that the distributions are identical and distributed and independent. So that's the typical assumption of machine learning. This is typically very tough in federated settings because maybe the hospitals have different patient cohorts, different populations, and maybe also different ways how they acquire those images. So there's always, in practice, there's always a bias. And in order to address this, there are algorithms, for example, FedProx, which try to encourage the local training to stay as close to the global model as possible. So the way it's done, there is a kind of additional regularization term in the loss function. So as you can see here, we have the overall loss is a combination of the local loss, which you have in normal training, plus a second term. And the more the local weights diverge from the global model, the higher is this regularization term to motivate or to encourage the model to stay as close to the global model as possible. And then there are also options for adding additional security to the aggregation process. So some customers might say, okay, we are happy that the data is not shared, but we don't want that our parameters, the weights are analyzed or seen by anyone, not by the server or by other participants. So what you can do on top of the federated aggregation is what's called secure aggregation, which is a cryptographic protocol with a couple of options to increase privacy and security, which effectively ensures that the server or other participants are not able to see your, as a participant, your weights. So they can be aggregated, but until aggregation, they are not being able to be interpreted by anyone else. So this, for example, protects against man-in-the-middle attacks. But there is still an attack vector, which I already mentioned, because as I said, the training process is protected. But even if you use secure aggregation, you still get just a regular machine learning model. And this is subject to data leakage risks. Maybe in the federated learning scenario, even more than in the classic scenario, because you assume that the model is distributed. So there are more institutions who have access to the model. And as we have seen, so in particular in deep learning, it's possible to reconstruct training data to some extent. But what you can do to protect the model against these kinds of risks is to use differential privacy, which adds some carefully tuned amount of statistical noise to prevent any kind of model inversion or membership attacks. So this protects the model itself. And the federated learning library that we are using, Nvidia Flare, and you will see it in a couple of minutes, is able to add both of those protections. So you can use secure aggregation based on homomorphic encryption, and on top you can also add differential privacy to then protect the resulting model. So far about the federated learning concept itself. you will see it in action in a couple of minutes. I would like to briefly talk about the 3D brain tumor segmentation use case, which is the baseline of our demo. Here we are using Azure Machine Learning in conjunction with the Medical Open Network for AI, which is a specific network with a very interesting capabilities based on PyTorch for medical imaging when it comes to pre-processing, when it comes to the specific networks that are used in medical settings. So it's a very helpful network based on PyTorch, and we are using it in our central demo for 3D brain tumor segmentation, but also in the demo where we combine Azure Machine Learning, MONAI, and Nvidia Flare, which Harmke is going to show in a minute. So this is the use case. So if you think about an head examination in a MRI, for example, so what's typically what's happening is we are talking about 3D images, which means it's a stack of images which is generated, which are called slices, which represent different layers of the head as the scan is performed. So in our case, it's 155 stacked images, but it's not only one stack. Typically, the MRI is adjusted to generate what's called different MRI modalities. So adjustments means like working with different radio frequency pulses or adding a contrast agent, for example. And this is then helpful for visualizing different aspects. And these modalities have names like Flare, T1W, for example. So for example, in this Flare modality, this is relatively good for identifying abnormalities. T1W is good to visualize different structures of the brain, like the difference between white matter and gray matter. And then there is this modality which is called T1GD, which is a specific contrast agent which is added. And this is very helpful to visualize different structures of tumors, for example. So these are the features that we are using, the generated images. So for each patient, 4 stacks of images with 155 slices each. And then also the labels are very specific. So we have annotated tumor areas, so expert annotated tumor areas, which correspond to these 155 slices. And for medical use cases, different areas of the tumor can be interesting. So for example, here we see the whole tumor, which is the overall structure. It's the complete mass, including surrounding edema, so swelling, for example. Then we have the central part of the tumor, the solid part, which has the bulk of cancerous cells. That's called the tumor core. And then we have a peripheral structure around the core, which is called enhancing tumor structure, which is typically the part of the most aggressive tumor growth. And what I would like to do now is briefly show you how you can train such a model using Azure Machine Learning in a classical centralized fashion. And then Harmke is going to compare centralized training versus federated training. Harmke already mentioned that Azure Machine Learning provides different ways of authoring capabilities. So there is no code, there is low code. Here we are using a code first approach. You can use Visual Code Remote. So I'm currently using a compute instance on Azure Machine Learning. This is where the code is running, but I'm using Visual Studio code. You have other options as well, like Jupyter Lab, for example. So this is the central orchestration notebook for this use case. There is more specific training code behind it that we are not showing in the interest of time, but everything Everything is available in our invited to do so. Oops. Just seen that my notebook is gone. That's weird.
We had a slight glitch in the sound too.
Okay.
So I'm not sure if we lost
I
connection
think there was
for
a
minute.
network issue. Let's hope that it comes back soon. Yeah, I think there was a network issue. Let's give it a second.
Otherwise, we can first do the federated learning part of the demo.
Yeah, or let me maybe quickly look at if we can at least show the results here. Yeah, let's maybe look at the results of the experiment. So I explained the background already. So we are training a centralized model using Azure Machine Learning based on these modalities, on these stacks of images. We have the labels. So, and what is currently happening is I have in Azure Machine Learning also the capability of managing experiments. So we have our brain tumor segmentation experiment here. And as it's typically done in machine learning, you know, you have hyperparameters, you're trying out different things until you have a satisfying model. And this is happening here. So you can see these are runs of this experiment with different conditions, so different hyperparameters in terms of batch size, learning rate, for example. And what's happening here is this is a training run, which is currently ongoing. For the central training, we used 150 epochs up to 300 epochs. And what you can see here is every hyperparameter that we are using and also the outcomes, our metrics are stored and maintained here, including things that are important. So for example, I want to understand the pre-processing, because there is a pre-processing pipeline. So I want to really make sure that pre-processing works well as expected. So we can see our images here, and we can also see the corresponding labels. So I keep this with every experiment that I'm doing. So this looks good. And the experiment itself, as I said, it's currently running. I can see all the metrics I'm interested in, like the training loss, the validation loss, for example, and also there are specific metrics for segmentation which are important. So there is this concept of a DICE metric, which measures the degree of overlap between the ground truth segmentation, the expert segmentation, and also the predicted segmentation. And here you can see during the training process that not only the train loss is decreasing and the validation loss is decreasing, which is good, but we also see the degree of agreement between the predicted labels and the ground truth labels is increasing. And when we train for longer, we will see that it's converging towards 80, 90%, which we can already see here. So we have already a good agreement, which means our model is learning what it's supposed to learn. What we can also do, for example, if we are interested in the resource consumption side, here we are using a very powerful compute cluster from Azure Machine Learning, so a multi-GPU cluster with 4 A100 GPUs, which have 80 gigabyte of GPU memory each. So this is in particular for those medical imaging settings relevant, where we need a lot of compute power. And here we can see what's the GPU consumption, for example, what's the GPU energy usage, what's the memory usage here. For example, we could go further. We could even increase the batch size to improve the to utilize even more of our available GPU memory. All right, and I think in the interest of time, we should really switch to the federated training demo of Harmke. Sorry that I was not able to show you the notebook, but I think the overall use case is really clear, and now I'm really curious to see it, in particular in comparison, the centralized training versus the federated training based on Harmke's demo.
Thank you. Great, I can share my screen. Let me know if you can see it.
Mm-hmm.
Okay. So now we will move to the same scenario as Andreas mentioned. So we are using the same data set, the same model and parameters, but in this case, we have a federated setup. So just to give a quick overview of the overall solution that I will share later. First, let's start on the central part here on the slide. We have a federated server, which will do the aggregation of the local models that are being trained. And this federated server is also sending the training instructions. So this federated server will basically, by doing these aggregations, it will create the global model that will then be copied again to the local clients for the local training if another round is applicable. And then around that, we have these 4 different hospitals in different regions. So these would be mimicking different hospitals that have their own private data set to work with. So in this case, we not just have a central data set, but the overall brain tumor data set is actually split into 4 parts. And each hospital will have their own part to work with. And they will communicate just with the federated server to get the instructions to train their local model. And in this overall setup, there are actually 4 different machine learning workspaces involved. So this federated server is implemented with a machine learning workspace in Europe and also a data science virtual machine that is used as a server, which is in Europe. And then one of the clients is also in Europe, so this is connected to the same workspace. And the 3 other hospitals will have their own compute and workspace to work with to do the computation. And as we mentioned before, so this solution is using Azure Machine Learning, but also Nvidia Flare, basically to support this communication protocol and the federated applications. And we're also using Monai as a framework for part of the actual training task. So just a little bit on Nvidia Flare before we will start looking at the solution. So Nvidia Flare is an open source SDK for federated learning. So this is really useful to speed up the development of a federated learning use case. It offers capabilities both for local experimentation. So if you maybe have not all your infrastructure ready yet, but just want to experiment with federated learning. But on the other hand, it also supports use cases at scale with an actual federated setup. So that is quite useful. And it also has a lot of these workflows included that we will be using. So for example, the workflows to aggregate the weights using some of the different approaches that Andreas shared before. So with that, let's have a look at the notebook that we have developed for running this federated job. So now we are switching to our Azure Machine Learning workspace. In this case, it's the one in West Europe, so that we are using for orchestration. And let's have a quick look at the notebook. So we are importing some variables, some packages here, and we are start loading some variables. I think an important part here to mention, which is an important component in the overall solution, is the Flare project file. So this is one of the components of Nvidia Flare, where you basically define the overall setup of your federated application, as I would call it. So this is not yet on describing the training workflow or what we want to do in a machine learning use case, but in this case we're describing here the different participants. So we are describing our server and the 4 different hospitals that we are working with. And what we actually did for our use case is that we extended this project file a bit with some of the variables that we needed for our specific clients. So in our case, for example, we are storing the data path, and this is referring to where the data is stored, in this case on Azure. But it actually also supports on-prem or hybrid scenarios. So we could also refer to a data path of data that is stored on a local Kubernetes cluster, for example. So after loading this project file, the next important step is to generate startup kits. So this is another concept of Nvidia Flare that we are using. What will happen next is that for both the server and for the different clients, we will be spinning up Docker containers, and inside these Docker containers there's this Flare component running, and what exactly we are running inside these containers, that is what we are generating at this stage with these startup kits. So now we are generating them, and as the next stage we are actually uploading them to the different computes, but that happens later. So we are using here that project file that I just shared, and using the NVFlare provisioning command, we are generating the different startup packages, and we are loading that directory because we need it for reference to copy the packages later. We are also copying our training code, our actual application, to the admin directory inside this workspace. So it's good to know that the federated server actually both hosts the aggregation server as well as a Flare admin client that can be used to send the instructions to the server. And we can actually use the Flare API to send these instructions from our local notebook, but you will see that later. But for now, it's important that this admin has access to the training code that we need and the configuration. So that's why we are transferring it at this step. Unfortunately, during this session, we will not have the time to go in depth on the actual application code that we have, but just to give you a quick idea, I have the training code right here, and yeah, just to highlight, for example, the model that we are using. This is just one of the objects that we are importing from Monai. So as you can see, it's quite a complicated model architecture, but still we can just import it quite easily from Monai. So that was quite useful for us. And also for the transforms, we are also using objects that are available in Monai. And together with the training code, we are also sending some configuration files to the admin client at this stage. And just to give you an example of some of these configurations, so here we could define some of these hyperparameters, also this fedprox parameter that Andreas shared about, for example, but also where the data can be found. So at this stage, we have all this training code and configuration ready and copied on the admin. And then we will actually start submitting the admin packages. Here we're just doing some checks. We are also generating an Azure machine learning environment. So this is like the Docker image that we are using both on the clients and on the server. And we make sure to register this environment to all the workspaces that we are using in our solution. So both this West Europe workspace where we have just one client and our server, but we need the same environment in the other machine learning workspaces where the other clients are located. And then before we start doing the actual federated run, we start first with a simulator run. So the simulator is also part of the Flare SDK, and this is a capability I shared it before already that you can use for local experimentation of a federated setup, but then all in one compute. So in this case, we're using an Azure machine learning job, and you will see these occur later as well, because we are using these Azure machine learning jobs both for the simulator as well as sending the startup packages to the server and clients. And in this case, we're sending a job with our Nvidia Flare simulator command, where we are adding all the training code that we have and the workspace directory. So in this case, we have been using the simulator for our centralized experiment. So we are only using one hospital in this case for the purpose that we can compare it later with a setup with multiple clients in terms of the performance that we get at the end. So that is what I'm doing here, and maybe just to give you a quick insight in what you would get here. So this is again this experiment view, and we have our simulated round with 1 hospital and 200 rounds here, an experiment that we did. And if we then look at the metrics, then we see that again these DICE metrics, both the mean DICE and for these different type of tumor areas, we see all the metrics pop up here in the workspace. So that's for the simulated run, but now onto the actual federated run. So what we're doing here, we are starting the Flare server inside a container on the data science virtual machine that we are using for an aggregation server. So we're using another job command here, but in this case, the code that we're sending to the job is the startup package for the server. And as a command, we're just running the startup command to make sure that this Flare application is started inside the Docker container. And after running this and starting the server, the result will be that we have a machine learning job and that we have this Flare server that is ready to be connected to with our clients. So that's the next step. Here we will start our Flare clients using their deployment packages. So in this case, we have a for loop here where we loop over all the different clients that we have in our project.yaml file. And based on the appropriate workspace and compute name, we are spinning up different jobs. So one for each of them with the appropriate startup package for the clients. And after starting this, we have the Flare code that is running on the clients as well. And it will automatically try to connect to the server. So if that succeeds, then we actually have all the infrastructure ready to start our federated training run. So that's actually the next step. So in this case, now you will see that we will use the Flare API to connect to our admin client, as I mentioned before, running on the server, so we can start sending these training instructions. So we are now navigating to this admin directory and then using the API to connect to the runner. So this contains all the functions that we need to send these instructions. So for example, one of the functions that we can use is to check status. So in this case, the result is that we just have a table where we can verify that the different clients are all connected to the server so that we are ready to start our training job. And then the next step here is that we submit our actual training code, this time not to the simulator, but to our server, so that it will then distribute these instructions to the clients to start training their local hospitals. And what that looks like in Azure Machine Learning. So if we go back to our experiment here, we actually see that I have one of these jobs running. And with all the code that I've shown just before, we will have 2 jobs in this workspace. One is the server job. So if we click on that, then we will see that actually the logs for this federated server are in this case streamed to the outputs and logs section of this experiment. So that's quite useful. And we also see the metrics here that are generated by this experiment. So now that you see that so far 64 runs are finished, and while these runs take place, the metrics are actually streamed to Azure Machine Learning. So that's quite useful, that you can keep track of your federated experiment while it's taking place. And we have another job here for the hospital. So this is where the logs from the hospital run while it's training are actually streamed also to Azure ML. So what you could see here is maybe some logs that would give an indication on the performance of the local model, for example. So that's on the training and how that can be initiated. But I think it's also interesting to go back to the presentation and do an actual comparison in terms of the performance. So that's what you see on the current slide. So here we have the overview of the different tumor areas that are annotated in these images, and also the mean dice. So the red line here actually indicates the performance for the centralized run, and the blue line indicates the federated setup. So in this case, we had these 4 different hospitals. And it's probably a bit easier to show if we zoom in on these mean dice scores. So this is the mean across the different tumor areas that are annotated. And yeah, so this is quite interesting, and these are actually the results that we actually hope to see as well, because what you can see in this graph is that at the end, it shows similar performance between the federated and the centralized training run, although we need more epochs in the federated run to achieve the same performance. So that's what you see here. There's actually a delay in terms of the performance that we are achieving. But if we look at the end of the 200 runs that we did, then we see that we achieved a similar performance here. And that's it. That's all the content that we prepared for today. I think now I'm moving to the slide with some of the resources that you can have a look at if you're interested to learn more about this, maybe some background on federated learning, or to learn more about the use case itself. And with that, let's see if there are maybe some questions, if there's some time still to do a Q&A.